board. Okay, so I'll write down here number, chapter 27, number 17, you said?
Yeah.
All right. Good, 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 good. All right, let me read it here. Whoops, can't do that. What did I do? Okay. And let's see, I got these started. What do I do with the questions? Oh, those are the answers, I think. These are the questions. Okay, here we go. All right, so number 17 says, if the magnitude of the drift velocity of the free electrons in copper is, what is the electric field in the conductor? Oh, okay. Now, Ohm's law, if you will, on a microscopic level, and I'm drawing a blank at the moment here. Voltage is current times resistance.
Are you
Oh, I need to share my screen, huh?
Yeah.
Sorry. Here, yeah. Let me set that up. Get us going here. But also, let me grab the textbook because there's a little equation here where they introduce Ohm's law. And
Yeah, I tried to find like a relationship between drift velocity and electric field, and I found the current equals NAVDQ, but I couldn't find a place to plug in current, so that everything else canceled.
Good. You're at the right place. In fact, maybe I won't even get the textbook going. Maybe I'll just go right to the video and write that down. Okay, like what you said here. Let me okay, do a screen share. Let me go to my camera. Let me do first connection of the day. Here's a screen mirror connecting. Connecting and voila. All right. So I started scribbling some things here, but like I said, instead of trying to share the book with you, I just am going to say, if you look at equation 27.5, and I think this is what you read off, that the current density is the number of charged carriers, the charge of those charge carriers, and its drift velocity. And the other equation is Ohm's law on a microscopic level. And this was kind of his thinking. Ohm's law actually starts on a microscopic level and says that the current density is equal to conductivity times the electric field. Okay. So coming back to the question, I think the question said, what's the electric field, right? It says, if the magnitude of the drift velocity, what is the electric field? So using this equation 6, I would say, okay, so the electric field is the current density over the conductivity. And the current density then is this earlier equation, which is the number of carriers times the charge of each carrier times the drift velocity over the conductivity.
Mm-hmm.
All right, now
where I got lost.
Oh, okay, so you got that far and then got lost, huh?
Yeah.
And maybe there is an assumption here that you may not know, but they are assuming then, a little bit about, and then what's the material they gave us here? Copper. Because the first thing would be this N. How many carriers do you have? That might be the hardest part of this problem. So I'm gonna pause on that one for just a second. Okay. So let me just leave that alone for N. But since the carriers are the electron, the charge of those is 1.602 times 10 to the negative 19. The drift velocity is what they gave you, 7.84 times 10 to the negative 4. And then the easier one here is the conductivity of it. And here they just want you to jump back to the book and go to the table. What table is this? Table 2 is what I'm looking at. It's kind of small here on my screen. How do I adjust it to 100%? What happened to my home button? Oh, it's in an edit mode. Oh, don't want to do that. All right. Oh, there it is. Okay. So let me just make it a little more reasonable for me. So this number here, I guess, is what I'm going to do first before the harder one, n, and to say, okay, this is the reciprocal of the resistivity. And the resistivity is given. And so this would be 1 over 1.7 times 10 to the negative 8 for copper. And so that's just right out of the table. So 1 divided by 1.7 times 10 to the negative 8 comes out to be 5.88 times 10 to the 1, 2, 3, 4, 5, 6, 7. So 10 to the 7. All right. And that one too you might have got. I don't know.
Yeah.
Yeah.
I got all those numbers. It's just the n.
Yeah. Okay. So the n is going to be the hard one. All right. So let's do the n together here. The n is the, and I'm just going to write it this way, number of carriers per volume. Number of, I think the book used the word particles. So I'll just go number of particles. All right. Now, there's something that the book is kind of implying in here that you may not know. And that's when you have copper, and if I go to a periodic table here, I believe copper is atomic number 29. Yeah, 29. Mm-hmm. So copper would look something like this. It would have a nucleus, and I'm not going to try to draw all 29 protons in here, and then whatever the corresponding number of neutrons is. So that's the nucleus. Then it's loaded with 29 electrons, and only one of them leaves the copper atom and becomes part of the conductivity of it. In a chemistry class, we would call this the valence electron. Yeah. The other ones are hooked together. All right. So that's one thing that I don't know if you knew or not, but have to know that to figure out the n, then we're talking really more about the number of atoms per volume. Because even though there's 29 electrons, only one of them is going to come off and be part of it. Okay. So what you can do then is switch this into something like this. What is the mass per volume? And then what is the mass per one atom? And so when you were to take the mass per volume, which we call density, and then multiply it by the mass of one atom, or you probably could even write it this way: mass per volume divided by mass per atom. And so the mass per atom is what we call the density, although there's so many different kinds of density. As you know, we've been working a lot lately with charge density. This is mass density, okay? And then we need to know the mass per atom. Okay, so the mass density is something that you would look up. You would just Google it. It's in your book. If I go to your book, all these densities you saw in 121, and so you may not remember, but way back in chapter 14, I'm just going to click on 14 and see which table 1 is. Yeah, there it is, table 1. Table 1 is, make it 100% again, but table 1, and so it's on page like 391 of the Survey textbook anyways. It says that the density of copper is 8.92 times 10 to the third kilograms per cubic meter. So then the, I was playing with this. I thought the blue stood out a little better on this yellow paper I got. So then the mass per atom, now I got to go back to that periodic table and look up copper a little better. It looks like it's 63.6. So 63.6.
And that's from the periodic table. It's
yeah, that's what they call the atomic mass.
Yeah.
Okay. And so again, maybe that's a little unfair questions because both of these are asking you to go back to your chemistry a little bit. Now, not a real advanced chemistry, so it wouldn't be anything more than high school chemistry. But to know that there's one valence electron and to know that I can get the mass on the periodic table. Now, of course, this is the other thing. You've got to be careful. This is in atomic mass units per. So I need to, and I'll just leave the top alone for a moment. But then the 63 point, whoops, I meant to put AMU, atomic mass units. I put atmosphere, probably because I went back to chapter 14 and I saw the unit of pressure there. But 63.6 atomic mass units per atom. And then I'll also have to recall that an atomic mass unit is 1.67 times 10 to the negative 27 kilograms. So on the bottom here, the atomic mass units will cancel off, and I will now have kilograms per atom. And then the kilograms will cancel off, and I will have then atom, or plural atoms, per cubic meter once I do the math here. So that's really your question right there. And so in the denominator, just to do the numbers, I'll go, okay, 63.6 times 1.67 times 10 to the negative 27. And so that would be the mass, that would be the number in the denominator. So let me just write the numerator, 8.92 times 10 to the third, then divide that by the last answer. And so we are looking at 8 points, like it would be a 40 atoms per cubic meter. And so now I can finally come back and finish this calculation. Lay this on top. And so now the electric field would be, so there's my N. Oh, I forgot to write times 10 to the 28th, sorry. So this would be 8.40 times 10 to the 28. This would be the 1.602 times 10 to the negative 19. This is the 7.84 times 10 to the minus 4. And then this is that 5.88 times 10 to the 7 that we got a little earlier. So first number is already in my calculator, 1.602 times 10 to the negative 19 times 7.84 times 10 to the negative 4, then divided by 5.88 times 10 to the 7th. And I got a 0.18, and I suppose I should have followed my units carefully. But let's see, this would be atoms per cubic meter, and atoms isn't a real unit, it's just kind of a clarifier, so I'll cross that out. This would be the, or particles, because in this one here would be coulombs per particle, or per atom, so that's how the atoms would cancel off. This one was in meters per second. Oh, and the units for the, well, they listed at resistivity. So if we take the reciprocal of that for the conductivity, let's see, what did they list? I left it. I think it was ohm per meter. Let me just double check that. Chapter 27, table 2, I believe it was. Yeah, ohm meter, not per meter. But yeah, so this would be the inverse of ohm, and then the inverse of meter, and then that would be perfect, because that would then be an ohm over, yeah, and then a coulomb, yeah. So I didn't do a very good job with the units there, but I will if you want. But anyways, I think, and I should, now that I have the solutions called up, I probably should check the solutions. Chapter homework solutions, chapter 27. And then scrolling down here to number 17. Yep, 0.18. Oh, although they put it in volts, and that's probably better, volts per meter, because they got the ohm. And then when you,
Oh, yeah.
Write it with the ohms, you might want to go, because you got the coulomb per second. See, the coulomb per second is an amp. And so this right here, the coulomb per second is an amp, and then this is an inverse ohm, and so an amp times an ohm is a volt, and then you're left with that meter. So, but coulomb, a Newton per coulomb and a volt per meter are the same units. So,
yeah,
but I probably digressed there, because your real question was really about N.
Yeah, I know all that chemistry, but I just would have never related it.
Oh, there's a good question. Why not? You don't want to forget all that chemistry. Or
Yeah.
maybe you want to. You shouldn't forget all that chemistry.
Right. I really shouldn't, because I have to take it next semester.
When 55?
Yeah, 55.
Yeah, because you'll probably have to do the sequence 55, 56?
No, I was supposed to do 55 this semester and then 56 next semester, but my 55 section got canceled. And I couldn't fit in another one.
Huh. I wonder why they canceled it. Is there not enough students, or?
No, there was plenty. All the sections were filled. But they had to, because the school went to they were going to do partially online for chemistry labs. They were going to have chemistry labs in school.
Oh, they were, okay.
But then they canceled when things didn't get better, they canceled the in-person labs. So the chem, whatever, they reorganized the whole class and the whole schedule. And two of like the 10 sections, however many there are, one of which was my section, got canceled entirely.
That's a bummer for you.
Yeah.
Yeah. Do you ultimately have to do 156 to transfer?
No, it's highly recommended.
But it's one of those. Yeah.
But it's not required at any of the schools that I'm applying to, so I'm just gonna go without it and see what happens.
Yeah. I like the way they list that on the transferring thing. They say these are required and these are recommended or highly recommended.
Yeah.
With the idea that, at least you could at least you could apply and kind of know what they're looking for. And know they're looking for, you must have these, and we prefer you had these other ones. And so if you don't get accepted,
some of the classes aren't even offered at this school, like materials things. That's not offered here, but it's like a required course at some of the schools, which is interesting.
Yeah, but it's required when you get there, and that's kind of normal for a community college.
Yeah.
So you'll end up taking it there.
Mm-hmm.
And the engineering transfer, they even have something different besides just having a list that says these are required and these are recommended. They then have kind of a placement that says that if it's not taught at your school, this, we won't factor that in as a problem for your admission. We'll understand that, well, you couldn't take it. It wasn't offered.
Right. Yeah, that's exact. I think that's what my counselor intends while I'm transferring.
Good.
We'll see what happens next semester. It should be mostly okay, because there's also the tag program. If the classes that I didn't take have any sort of limitation on if I get in or not, but we'll see.
Now wait, I was under the impression that the tags. Well, what's your major? I understand the tags were all canceled for the the engineering majors. Is that not true?
Well, it let me apply for it, so.
What school?
Irvine.
Oh, okay.
Yeah, the application went through fine. They didn't say anything about it.
Oh, okay, very good.
Yeah.
Good. Yeah, maybe I was misinformed, or maybe they're bringing them back. I don't know. Or maybe it was some combination of that. Maybe not all the schools eliminated it.
Yeah. Oh, here's a quick question. An ohmic, it's a material that is valid with Ohm's law.
Okay, yeah.
What is the opposite of an ohmic?
I was trying to kind of explain this kind of at the end of the video on the Ohm's Law lab. I don't know if you've gotten that far, but if you take Ohm's Law, what we call its macroscopic form, voltage equals current times resistance. Materials that keep the same resistance when you turn up the voltage or turn down the voltage, we like to say that is an ohmic material. Okay, so if I were to make a graph, again, just like you did in the lab, where you have some kind of power supply where you can change its voltage. And so if you up the voltage, you up the current, and it always does it by the same factor. That means this resistance here would be a constant. On a graph, you would get a straight line.
Mm-hmm.
And of course, what that means, if you were to take the voltage and divide it by the current, you would always get that same number. And that's what we saw with the blue and the red resistor in the lab.
Yeah.
They always kept the same. The truth, though, is when you turn up the voltage, they have more current, and the more current makes them hotter. And so nothing really keeps the same resistance. Sometimes it's not noticeable until you get to really, 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 really high temperatures.
Mm-hmm.
And so what we did in the class for the light bulb, I took the light bulb and I measured the resistance and got a slope, something that looked like this when it was kind of low voltage and cool. And I didn't really plot the stuff in between, but if I did, it would kind of have a curve like that. I did this stuff up here at 5 volts.
Yeah, and it was higher, yeah.
Okay, and you were to notice that the resistance changed. So something like that, we would say it's non-ohmic. It changed.
Okay, so there's no term for non-ohmic material.
Well, that is the term. It's either ohmic or non-ohmic. So it's either ohmic, and so it stays a constant regardless of how much voltage, or it's non-ohmic and it changes. And even then, you could argue that there is no such thing as purely ohmic. Everything changes its resistance. The question is, does it change enough to be relevant for what you are using it for?
So is temperature like the primary factor?
Definitely, temperature is a primary factor. And there's smaller things, like even air pressure can change it.
Yeah.
Humidity can change them. But those are usually very, very minor. It's temperature that's the most obvious role.
Interesting.
Yeah.
A
lot of things in life, it's not one or the other. It's not ohmic or non-ohmic. It is just really a matter of how non-ohmic is it, because everything is curved a little bit, and then it's just a matter of what are you working with. If you're working in a small range, you won't even notice it's a curve, and therefore you'll call it ohmic.
Yeah. Here's one last conceptual question. So I'm in the 117, the circuits class.
Oh, you're in that class too. Good. Yeah. Good.
And
I hope it'll make this stuff easy for you then.
Yeah, actually, I think that coming up, if we continue on with the applications units, these next couple of units, what I'm doing in 117 should be helpful.
Oh, yeah, because the next chapter, you'll see here Sunday night when I send out a message and you start reading chapter 28, you'll see all these things you've been doing. You may not have been doing kind of this chapter 27 where you get down into the physics and the microscopic view of them, but you'll be doing the solving of them, which we're about to do, things like Kirchhoff's first and second law, and and doing
are we doing node calculations?
Yeah. So it's the Kirchhoff's node rule. We will call his second rule, I think. I don't think we'll call it the node rule. We'll just call it his second rule.
Okay.
And I think you call it
KVL and KCL.
Okay, yeah. So you call that one KCL, and then the KVL is referred to as Kirchhoff's voltage loop rule. And then since this is a physics class, I'll probably you'll hear me in the book spend some time justifying why it works.
Right.
Conservation of energy is really the bottom line.
Yeah.
And then use it over and over again to solve for current in complex circuits.
Are we going to be doing the super nodes?
No, we won't quite go that far. That's your. I could probably be safe to say that everything you're really doing in that circuits class is founded in conservation of energy and conservation of charge. And so that's the physics part of circuits. And then you are going to learn different techniques. Of course, the easiest one, and I think you've already learned this, and you're going to see this right away in chapter 28, is looking at series and parallels.
Yeah. Well, that was like the first thing we did.
Yeah. And then so we'll do that first. Then we will look at the Kirchhoff's laws, what you call the KVL and the KCL. And that's about as far as we'll go. Because then you'll go, in your circuits, you'll go on and just start doing supernodes, and you'll probably do mesh currents.
Yeah, we actually just, we did mesh currents.
Okay.
2 days ago. So.
Okay. Yeah. So you'll go on to learn more techniques, but the truth is all of those techniques in terms of physics, in terms of science, is just a conservation of energy and conservation of charge, and it's just trying to give you a technique that will allow you to both quickly and easily solve.
Yeah.
Yeah. So
I mean, that was like it was like problem 4 from the exam, just the longer process.
Yeah, and it's kind of an interesting technique too, because you probably in your circuits class haven't even done capacitors yet, right?
No, we haven't.
Yeah. So
this was first year, which was like confusing for me. I was doing resistors at the same time in the other class.
Right. So from a fundamental microscopic, science point of view, it makes a whole lot more sense in terms of physics to talk about capacitors, because you talk about charge, and a capacitor is just storing charge.
Yeah.
And then that's a good reason to introduce series and parallel.
Mm-hmm. Well, I mean, the equations were the same for the capacitors anyway. That made it convenient. They were they're
the reverse of each other.
They were the reverse, but
yeah,
the same. It was like pretty much the same. I just had
right. So yeah, I always find it interesting, and so do students, because in your circuits class, you start off with these series and parallel, and you start with resistors.
Yeah.
And you don't really get into the physics of how they all work and that, but you get into more of the practical use of them. And so it makes more sense to start off with resistors than capacitors.
Yeah. Mm-hmm.
Well, of course, we're just doing exactly the opposite. Well, I shouldn't say the opposite, but we're approaching it a little different. We're approaching it from the fundamental science of it. Then it makes sense to do capacitors and use capacitors to introduce the student to series and parallel. So you're about to see series and parallel for resistors in chapter 28, but you'll see the book doesn't spend much time, nor do I spend much time, because it's assumed you kind of know what series and parallel is. It just, instead of putting capacitors there, we now put resistors there. And so that's kind of the first half of the chapter coming up, and then we'll get into the KVL and the KCL.
So in that circuits class, and even now after we did the Ohm's Law lab, I've noticed that all these resistors seem to have the exact same margin of error, always in the downward direction. They always undercut the amount. Every resistor that I've measured for that class, and I have like 50 resistors, is always under by like the same percentage.
Really?
Yeah, it's so, I don't know if there's like any reason for it, but they're all the same. And like even when we did the lab, the resistors that you measured were both like about it was a few percent lower. Yeah, and it was like the exact same as the resistors I have in my box over here for engineering.
It's not completely random, and maybe that's it. Is again, these things are mass produced.
Yeah.
And it would be too expensive to try to get them on exactly, if they say 100 ohms, to make it exactly 100 ohms.
Mm-hmm.
And it turns out it's not that critical. So the fact that they're all lower is a little bit of a surprise. But they kind of anticipate that a little bit. In other words, if you took a brand new set of them, you wouldn't have half of them below and half of them above. You do get most of them below, because what happens with time is they get abused with heat and then they start to rise in their temperature. And so they do take a little bit of that into effect by deliberately trying to shoot that the average they produce is lower than their markings. And with time, they will become a little higher than their average.
Okay.
And so they'll stay within that 10% range for their lifetime.
That makes sense.
But we do have some that are above. So, in my case, I would say it's just coincidental.
Yeah.
Now, if you also noticed, ours were, even though they were below, they were barely below, right?
Yeah, they were about, what, like 1% below? I wrote it down somewhere.
Yeah. What I've done in the past is when we buy a new box of them, I just go through and measure them, and anything that's significantly off, I just throw away. They're so cheap. Yeah. And so the only things that we have left in our lab are ones that are, within 1 or 2%, even though they could have been off by 5% or more. If they were, I threw those away. So we don't come across them. Now, you guys in your circuits class, you buy a kit, so yours, I think, could be anything.
Yeah, well, this kit has been really something else. It came with the voltmeter, came with a dead battery and a blown fuse. I had to replace both of them. This screwdriver they gave us to turn the potentiometer. Oh, yeah. The little metal part that's the screwdriver is like inside of the plastic, so you can't actually use it. It was like it was made like too far in, so you can't use it.
Quality stuff.
Yeah, the alligator clips, the rubber part slides all around, so you can't actually squeeze it. It's some work to do those labs at night.
Oh, that's okay. That's kind of funny. Probably not when you're trying to work with them, but
well, it was the first. Every lab since the first lab has been fine. I've gotten it done pretty quickly. But that first lab, I didn't know that the fuse was broken.
Yeah, right.
My current measurements, I was getting like all kinds of weird stuff, and I sat there until like 10:30 at night trying to figure it out, but it wasn't working. And then I just put it all away. And the next day I got it back out. I was like, all right, we're gonna see what's wrong this time. And I found there was a bag of extra fuses, and I was like, okay, well, this is probably exactly what's wrong with it.
Yeah.
I did it all the next day, but man, that was an infuriating night that first day.
Okay. Yeah. Interesting.
Well, I have engineering soon.
Oh, yeah. That's right.
I'm going to get some.
Not too many questions today, but you never know.
I just started the homework for this chapter. Mm-hmm. I did all the videos in the lab. Mm-hmm. I just started the homework, so I don't have that many questions yet. But
well, you guys spent so much time, I would assume, getting ready for the test that.
Oh yeah.
I kind of figured that the rest of this week, people were either recovering or doing catch up for the other classes they put off.
Yeah.
As you can see,
I had the engineering 115 exam was Friday, just before the exam for this class. So I had to get ready for that one, and then the physics exam.
Okay.
And so this week now, the aftermath has been remarkable.
Yeah. That's good. Yeah, it seems to always work that way. Sometimes students, I think, accuse us of trying to throw all the tests at the same time, because math does the same thing. We usually
you do 3 tests, and it's after like 5 or 6.
Yeah, we just count. We go, well, the semester's 15 weeks. We give 3 tests, so why don't we just do 5 weeks and have a test? I mean, what?
Yeah, and then all of the teachers do it, so you have 2 or 3.
Right.
1 week.
Right. So we don't coordinate it to make it hard on students, but it ends up being like that because all the teachers are just
Yeah.
now. Now there is a little difference to that. Um, when I teach 121, I do a little different. I do 4 weeks of test, 4 weeks of test, 4 weeks of test, and
And a couple of weeks final, right?
yeah, and then a couple of weeks of kind of what I'll call minor chapters, that fluid chapter, and then a review. So that one's a little different, and so, uh, but my other two classes, 121 and 122, I just count 5 weeks. So.
Yeah. So 123 next semester.
Next semester, yeah.
It's considered easier than this class by people. Right.
Yeah, most people say that. I agree. It's also structured a lot different in the sense that we don't do one topic for the whole semester like we're doing here in 122. 122, we start with electricity, which naturally leads into magnetism, which then leads into the two together, electricity and magnetism. Mm-hmm. So each chapter kind of builds on itself. It gets more advanced. 121 was the same way. We started with one-dimensional motion, went to two-dimensional motion. We went to Newton's laws. We went to energy. We went to rotation. And it was all mechanics, and it just got harder and harder and more advanced, each chapter building on itself. Mm-hmm. But 123, you could better think of that one as like 4 mini courses, because the first quarter of it is waves. Yeah. The next quarter of it is thermodynamics. The next quarter of it is optics. And the next quarter of it is modern physics. And so we completely change. And that, that's good and bad. It's, if we're working on a topic that you really like and we change, you're going to be kind of bummed. Although if we're working with a topic you're not enjoying or don't understand and we change, that's good. Yeah. Also, good and bad is by the time we do about 4 chapters, say on optics, right when we get to really what I'll call the good complicated stuff, we leave. So the good thing is we don't really get to the complicated stuff. The bad news is that means we're also not really getting to the practical, the application, the stuff that, okay, how am I going to use this in the real world? And so
what do we learn in modern physics, the modern physics section?
Oh, modern physics is considered this revolutionary discoveries starting at about 1900. So, and that's broken down into 2 things, Einstein's relativity and Planck and others, Schrodinger, quantum mechanics.
Okay.
Yeah. So,
all right. Well, I'm gonna head out. I might come back this afternoon after engineering.
All right.
I have some questions on the homework. Thank you.
All right. Take care.
See you later.
How's it going, Dr. Young?
Hey, good. How you doing?
Good. I've got a question for you from 121.
Ah, good.
Do you want me to maybe share my screen so you can see it? It's kind of a lengthy question.
I do here. Let me, let's see, go back to stop sharing mine. Hello, stop sharing. Okay, there we go. And then I'll write this down in my notes, 121.
So right now it says that you have disabled screen sharing when I try to share my screen.
Oh, that is true. Not by purpose, but by default. Let me change that. Here we go. Forgot about that. Okay, try it again.
Okay, perfect. Share. So let me see here. So here she is.
I like that. In fact, as long as I got it on the screen, I'm going to do a little screen capture of that. This one looks like it might be kind of involved, and I might want to come back to it. Let's see. Nice. It said I copied it to my clipboard. Let's see, where should I put it? How about, oh, I'll just start. How about Word? And nice. Okay. Let's see. It says, so block number 1 with a mass of 6.28 is attached to block number 2. Oh, you know what? As long as I did that, maybe now I could take advantage here. So instead of me reading it, I'll go ahead and start switching back over to my camera. And I'll read it and draw the picture. That might be helpful. Oh, get to my camera. All right, now, hopefully without losing that, but I'll change my screen here. All right, so you have, it looks like an incline here. And you have block number 1, mass of 6.82. It is attached to block number 2 with a string. Block number 1 is placed on a ramp. Okay, so this, the one, number 1 is the one on the ramp. The diagram labels it as a capital M and 6.82. The string goes up, goes around a pulley, and then comes down to another block, which is labeled as lowercase m. So block number 1 on a ramp, tilted at, and so here's an angle of 29.4 degrees. It has a static coefficient of friction, so mu sub s of 0.388. The string runs over a massless, frictionless pulley, and block number 2 hangs straight down. The minimum mass of block number 2 can have without the block moving is m sub minimum, okay. The maximum mass block number 2 can have without the block moving is okay.
I struggle with that too. You know, it's like it's either going to move one way or the other way based
Yeah.
on, you know, a minimum or a maximum.
Got it. Yeah, that took me a second to digest. So yeah. Okay, I see. So it's going to go one way or the other.
Less time than me, I'll tell you that much.
Okay. Well, okay. Well, I guess that's good, but it probably took me still longer than it probably should have. Okay, so, and then I always get confused with his questions here because he doesn't have a question mark, but I guess it's to find the minimum and then also find the maximum, right?
Yeah, that's the idea.
Okay. All right, good. So I'm going to come back to my Zoom. Whoops. Get back to my Zoom meeting so I can kind of see what you're seeing. There we go. See my hand? Okay, good.
Yep.
All right. So here's the picture, and the I guess the first part of the problem, I guess I will do is to say, I'm debating if I should do maximum or minimum first. Maybe I'll do maximum, because if this is then the maximum here, it was just getting ready to pull it up the hill.
Mm-hmm.
Whereas, as you pointed out, minimum is just getting ready to go down the hill. So I'll just say, let's do the M sub maximum first, because I do want to show you that there's a lot of similarities between minimum and maximum. So we're not going to have to really do this all over again a second time.
Okay.
Okay. But let's not worry about minimum for a second. So then I would say, let's do a free body diagram for the one on the incline, which they call number one. But then also I'll do a free body diagram for number 2. All right. So number 1, there would be the pulling up the hill by the tension in this rope or string, I forget now what he called it, over the pulley. Then, and I kind of got out of the order I like to do. I like to say, to find all these forces, because you don't want to miss any of them, is to start off with the first one, which is its weight, gravity, and then everything touching it. So I should have labeled this one first, because that's just my normal pattern. It doesn't matter, of course. But so I'll do the weight one. Then the things touching it would be this rope. The other thing touching it would be the surface of this incline. And it's doing 2 things. It's pushing up on it, so that's the normal force. And it's also pushing back, keeping it from going uphill. Now, just to kind of get you ready for the next step, if you will, when we go to solve this for minimum, the only difference then in my free body diagram would be that the force of friction would be up the hill, because now it's getting ready to slide down the hill.
Gotcha. Okay. Interesting.
That actually might be the hardest part of this problem, is to recognizing which way the friction is. The friction is always opposite to the way it moves, but in this case, it's not moving. So we say it a little different. We say the friction is in the direction that's keeping it from moving. In other words, which way would it have gone without that friction? Yeah. And so maybe I wonder how this would show up in blue if I just put a force like this up the hill. And maybe I'll confuse you, but because I'm not trying to say that the frictional force is both directions. I'm trying to say it's down the incline when I have weight number 2 really heavy and it's trying to pull it up, but it's up the incline when mass number 1 is really heavy and it's, I don't know if endangers the right word, but it's...
Yeah, so the arrow pointing down is my FS max and the arrow pointing up is my FS min, sort of? Is that...
Yeah, and I hesitate with that word, max and min, because I don't want you to think that's the maximum or minimum amount of friction. That's the friction I get when I have the maximum or minimum weight on number 1. No, I mean number 2.
Okay.
And actually, let me expand on that, because this is going to lead into an important clarification here. Let me focus on this force of static friction, because static friction is an inequality. The static friction can be up to this value. It could be less than or equal to this value. So here's where the question becomes a big piece of physics here, where it says, okay, if you remember, the question did not say what mass can you hang here. It says what is the most weight you can hold.
Yeah.
So coming back to this free body diagram, you would be talking about the maximum weight when the frictional force was at its maximum.
Okay.
And I'm going to say that a second time when we get back to the minimum weight, okay? But I do want to point out then that you got to be careful with these static friction ones, because the static friction does not always have to be its maximum value. This does not have to be an equality sign. It does for this problem. This problem, it has to be an equality because the problem deliberately said, what is the most weight I could hold? And the most weight you could hold up here at number 2 is when the frictional force is at its maximum. So that's why I'm going to make this very important step by changing it from an inequality to an equality as I move forward in the question. And maybe when we get some numbers at the end, I'll come back and readdress that, to maybe try to help you understand that. But that's a big piece. Now, let me come over here before I start writing out the equations and do the free body diagram for block number 2. And as I said, I like to do the weight first and everything touching it. And this one's a lot easier. The only thing touching it is the rope there that's hanging over the pulley. So there's just those 2 forces. Oh, by the way, I kind of messed up in my diagram. Let me come back over here to free body diagram number 1. I should have used a capital M over here. So that should be a capital M, and this should be the lowercase m.
Why are those different?
That because I'm talking about the 2 different blocks. This is the force on the.
You're just delineating one mass from the other. Okay.
Yeah, and that diagram you showed me, your author said the one on the ramp. I called it number 1, but labeled it as capital M.
Gotcha.
So I should put a capital M with number 1, and then the one hanging by default would be number 2, and then the diagram labeled it as a lowercase m.
Yeah, and in my free body that I had drawn, I just went with M1 and M2.
Oh, okay, and that might be more clear.
Yeah.
I actually like 1 and 2, but like I said, since your picture used capital M and lower M, I thought, well, I better go with that.
Mm-hmm.
Okay, so to me, all these problems are kind of chopped into 4 steps. And we've done 2 of them. Here's what I like to say. Step 1 was right here. Do you get a kind of a good physical idea and a good physical picture in your head of what's going on? And we did that when we said, okay, you're going to put weight on here until it's real heavy and it starts to then go down, which pulls us up. Or the other way, you're going to take weights off till it gets to its minimum. Then it's going to get so light that this heavier weight on the incline is going to go down. And that was our, what I'd call step 1. Step 2 is to draw the free body diagrams. And if you actually do those 2 steps well, the rest of the problem falls into place. And what I call step number 3 is now write out the equations that are based upon these free body diagrams. And then step number 4 is just math, solve those equations.
Okay, so when I originally drew my free body diagram, I've since erased it and sort of just copied down what you have. But I had my axis shifted so that X was pointed up the ramp.
Which is a good idea.
And so then like I had my normal pointing out from the ramp, but then I had the force acting on the box being mg cosine theta.
Say that last phrase.
Well, so like that force that you've got pulling down on box 1.
Yeah.
I had it pulling, opposite of the normal and I had
Yeah.
its magnitude as mg cosine theta.
Ah, oh, perfect, perfect.
Okay, cool.
Watch. Okay, no, I think what you did is exactly what I'm about to do,
Okay, cool.
because let me just keep going with this. I'll maybe shift to another piece of paper. Oh, it looks like the red might not have been a good idea. It goes all the way through the yellow paper here. Maybe maybe I'll kind of see if I can protect it, but I like how the red stands out.
It is easy to see.
I think what you're saying then is what I call step number 3. Then step number 3 here is like it says, okay, let's go ahead now and actually then write out the equations. And to do that, this is what you were saying, you need a grid. You need an X and a Y axis.
Mm-hmm.
And so coming back to this free body diagram, and maybe in blue, I like to do this. I like to call the x-axis the directions, when you have something like this, that the two are moving. So what you're saying here is this one is accelerating up. Okay? So let's call that the x-axis, which then by default makes the y-axis perpendicular. And I will tell you from experience that if you know the direction of the acceleration, make one of your axes the direction of that acceleration, and the problems are mathematically easier, okay? So you don't have to, but if you make them so that the direction of the acceleration is the x-axis or the y-axis, usually just pick the x-axis, you will get easier equations. So I'm going to do that, and I think that's what you were saying you did.
Yeah.
Now I'm even going to do this. This might look a little weird, but I hope you'll let me. On box number 2, I'm going to call then down the positive x-axis. That's certainly not normal, but that's the way it moves. So that means by default, perpendicular to that is the y-axis.
So I'd be curious just your opinion, because the way my brain, I struggle a little bit with flipping the axis, but I don't struggle as much with just like flipping the free body diagram. So for some reason, I've been leaving my axis normal, and I just like said, all right, I'm going to have mg pull to the right. Does that make sense? Like, so that, or for the second one, right? So it would be like mg, gravity is now just a force pulling right, and the x-axis still goes right.
Oh, okay. So you're kind of doing this, which is fine.
I flipped the free body diagram. Exactly.
Yeah. And that's fine.
Okay, cool.
Yeah. Nothing wrong with that.
Okay.
Of course.
Cool. Do it the way you're doing it, obviously, but I was just curious if I was going to get myself into a bunch of trouble doing that. Because for some reason, my brain seems better at wrapping itself around that idea.
Yeah, I know. To me, I guess it's just kind of the same. And I think actually after you do these for a while, you'll kind of just go, well, yeah, that's the same. And you'll probably even maybe even leave this and start doing this. Who knows?
Okay, cool.
Okay. But I will tell you that I do this because it's nice for me to then know that the motion on the x-axis for object number 1 goes together with the x motion of number 2. And it just makes things a little easier in my mind that x's go with x's. If I didn't switch my axis, then I would be saying something like this. The motion of this one on the x-axis is the same as the motion in the negative y-axis.
Yeah.
And that, there's nothing wrong with that either. It's just another step that I got to keep track of that. Okay, now how does number 2 compare to number 1? So I always recommend to students to pick the x-axis, the direction it's accelerating, and make it the same for both objects. So that's what I'm sharing with you. All right. So that's kind of that first step here of number 3, where I gotta put a grid on here, and so now I can start writing out the equations. So let me do block number 1 here. I'll even divide block number 1 into x and y. I'm going to do the same thing for block number 2 also in a second, although it'll be easier for block number 2. Block number 1 is the hard one here. All right, so here's what I'm saying here. We know, and this is the whole point of where you are in the semester, that the sum of all the forces in the x direction equal the mass times the acceleration in the x direction. And I'll do the same thing for the y direction. The sum of all the forces in the y direction equal the mass times the acceleration in the y direction. And so again, this is what I mean by step 3, write out the equation. All right, so this step 3 should be fairly easy if we've got a good free body diagram. So let's take a look here. What forces or components of the forces are in the x direction? Well, clearly the tension is, but the normal force is all y direction. The frictional force is all negative x direction. And the gravitational is, as you pointed out, has components of x and y. So I'll start with the easy one, which is the T for the tension. Then I will say minus the force of friction. And so that's that one and that one. And I'll just repeat, the normal one doesn't have a component in the x direction, so I'll leave that one alone. But this might be the harder one, and maybe drawing its components here on the diagram would be nice. There would be this plus this, and so I'll draw lines along the y-axis and along the x-axis. And as you pointed out earlier, this angle in here would be theta, so this would be mg cosine theta for the part that is in the y-axis. And so the part that is on the x-axis would be mg sine theta. And that's the part I want right now. I want this part here that is in the x-axis. So I would write this as a minus, because it's in the negative x direction, mg sine theta.
Okay.
And then that has to equal
0, right?
Ah, good. And why 0?
Because the acceleration, we're wanting it to not be moving.
Right, we want it to not be moving. But also, and I'll take one more step here, but I'm getting a little too far into step 4, which is solving this equation. But as we said earlier, then this friction is then equal to the coefficient of friction times the normal when it is just on the verge of getting ready to move, but still not moving. So still not moving means the acceleration is 0, but on the verge of getting ready to move means we've got the friction at its maximum. So this is what I mean by step 3. Write out the equations. And this tends to be the hardest part for the beginning student, but I try to emphasize that this should actually fall into place if you've got a good free body diagram to look at.
Yeah, my issue was that I missed the tension force in my original free body diagram. So I had the mu n and the mg sine theta pulling opposite. It wasn't right, but this makes total sense to me now.
Okay, good. Now, also, let's do the y direction for this box number 1. And so again, come look at this free body diagram. The normal is clearly all in the y direction.
Mm-hmm.
And we kind of stated earlier that the tension and the friction is only in the x direction. But the force of gravity, the mg, does have a component in the y direction. This is that mg cosine theta.
Mm-hmm.
So with that in mind, if I were to write out the forces, I would have normal in the positive direction and a negative mg cosine theta for the component of gravity in the negative y direction. And that would be it as far as the forces in the y direction, because the tension and the friction are only in the x direction. And then, of course, as you said earlier, this MA would be a 0 because it's not accelerating in the y direction. In fact, even if it was going up or down the incline, the acceleration in the y direction would be 0. If it was accelerating up or down the incline, it would have an acceleration in the x direction, but not in the y direction. And let me leave it like that for just a moment, because I'm tempted to start solving these, but that's really my step 4. So I'm going to hold off for just a second.
Okay.
And say, all right, let me, maybe halfway down the page, look at block number 2. And I guess for completeness, I'll do the same thing for block number 2, X and Y. But if we look at the free body diagram for number 2,
it's just going to be an X.
Yeah, this part for the Y that says add up the sum of the forces in the Y direction and set it equal to the mass times the acceleration. Well, there's no forces with no acceleration. Yay!
Yeah.
And so that's really kind of a waste of time, but I wanted you to see it, and until you get familiar with it, it's nice to at least write it down and say, yeah, that's not needed. Now, okay, now I can go to the X direction. And so right here, and I call down positive. So when I say add up all the forces in the X direction and set it equal to mass times acceleration in the X direction, I would say, okay, what's going down is mg, and it's little mg. What's pulling it up, which I've called the negative direction, is the tension. As you said, we're setting this up so we're right on the verge of beginning to move, but not actually moving. So the acceleration would be 0. And not only do I want to put a 0 there, but that phrase that I'm right at the verge of moving means that this little m is the maximum.
Mm-hmm.
All right. So I'll say it again just to kind of drive my point home. But to me, there's 4 steps in this problem. Step 1, good physical picture of what's going on. Step 2, good free body diagrams. Step 3, and that's what we just did on this page, is to write out the equations from Newton's second law associated with this free body diagram. And now we can actually then do the last step, which is solve.
Mm-hmm.
So when I go to solve, maybe I'll start here by saying, this says that the tension is equal to mg, where m is this maximum. So that might be my first step of mathematics. That's kind of equal to this one over here. The first block and the equation from the y motion would say the normal force is capital mg sine of theta.
Mm-hmm.
And if I use both of those answers and substitute them, I finally got that fly buzzing me, and go back to this equation. So for tension right here, I would put m max g minus static friction times the normal, which we just said was mg sine theta, minus capital MG sine theta equals 0.
Isn't the normal mg cosine theta?
Oh, yeah, sorry, right here I copied it wrong. Thank you.
Mm-hmm.
And so that means right here should be cosine. Good. Good eye. All right, so now, I hope I don't take a too big of math step here. I can actually then solve, because these two negatives I'm going to bring to the other side of the equation and they'll become positive.
And then divide it by the gravity, essentially?
Yeah. And I'll divide it by the g. But the each of these have an mg in them. So I'll also factor out the mg. That's why I said I hope I'm not taking too big of a math.
I'm with you.
Yep. Okay, good. In fact, I'm probably not doing a good example because I wouldn't encourage a big math step during an exam. It's just too easy to make a mistake.
Yeah.
So just take little steps. I just kind of wanted to see if I could fit it on the same page.
Totally.
And then I think it would look cleaner on a video. But let's see if I did that right. So the m and g factors out, the mu cosine theta, sine theta, then divide by the g, and then the last step would be to say that g's cancel off.
I actually think sometimes, I don't know, my math acumen is greater than my physics acumen. You know, I'm in 220 right now. I find actually I make more mistakes when I try to do little algebra step by step. It's like you just go and it all sort of works out sometimes.
Well, yeah, good point. You just by writing things down, and your head gets ahead of you. That's what happened, by here. Instead of writing cosine and sine, yeah, I just kind of was writing, as you said, writing too much. My head was ahead of myself. I was thinking what's going to happen next. All right, well, I'm kind of curious then. The numbers, let me switch back to the picture I copied because, I don't even think I need to do that. Never mind. I think I've got the numbers back here where the mass was the 6.82 times, and then it looks like we have the coefficient of friction. I think I wrote that down. There it is.
0.388, right?
Good. And then the cosine of, and it looks like it's 29.4 degrees. And I need to just check the mode of my calculator. I think I'm still in degrees. Yeah. Never really sure. Depend on who I helped last. Okay. So that's the close bracket for the angle. Then what was else here? Then, oh, see, I made an algebra mistake too. I told myself I'd bring them both over and change their sign, and I only changed one. Yeah, don't do that much, man. But that should be a plus then.
Yeah.
Yeah. Okay. I'm glad I noticed it as I was typing it in. Okay. And then plus the sine of the angle, sine of 29.4, close that and close that. And so if I type this all in right, and you might have already looked at the solution here.
I haven't looked at it yet, but I can check if we want to know if we're right.
And so I got 5.65 for the maximum.
Cosine of.
And actually, now that I think about it, maybe the number's not that important because anybody looking at the video, they all get different numbers, right?
Yeah, we all get different numbers.
Yeah.
Plus sine of times 6.82. Yeah, so I got 5.6. Let me see. I'll plug that into my software and see if that's right. That's my max. So M max equals 5.65 kilograms. Equals 5.65 kg. Yep, that's right.
Now watch this. This was a big thing I wanted you to see, especially when it came to test time, because back at our beginning of this problem, when we were going through what I call, again, step one, getting a good picture of what's going on, we were saying that the maximum would be so much weight on here that it would pull this or want to pull it up the hill. Whereas the minimum would be such little weight for number two that number one would begin to want to go down the hill.
And so if I'm correct, I've got the T minus the static friction. I would just change that to T plus the static friction.
Right. So all the way back to our free body diagram. Well, actually all the way back what you just said. So in this equation, and I'll do this, I'm going to circle it in blue, but you see this, this right here, this negative sign in front of the force of friction would now be a positive sign, which would now make this a positive sign, which would now make this a positive sign. So then when we get back to right here, when we moved it to the other side, there would be a negative in front of this coefficient of friction.
It would be a negative in front of the, yeah, okay, I see it. In front of the mu s cosine theta.
Right. So that would save us a lot of work by having to do everything over. And also watch this in your calculator. I like to go back then. And if you go second and enter, it gives you all of that equation back. And this is the part where we're talking about. If this right here had been a negative, and so I'm just going to go and change my calculator to insert mode and put a negative. And I suppose I should kind of double check, but I still got the mass out front. Now I have a negative in front of the coefficient of static friction, but I still got cosine. I still got the 29.4. I still got the plus sign of 29.4 degrees. And now I'll just hit enter. And so this, I'll keeping it maybe in blue, M sub minimum now would be 1.04.
Yeah, that's what I got too.
And I don't know, there's something to be said about having to go through it all from scratch a second time in terms of homework and, you know, going through what, you know, that memory muscle.
Mm-hmm.
But once you get that better, then it's, I think, more advanced to kind of see that it's just the opposite direction.
Mm-hmm.
Now, by the way, the comment I made at the beginning of this was, if I did the free body diagram for the minimum, then what would happen is the force of friction would be uphill, but at its maximum value. Did you catch that?
Sorry, say that one more time.
The force of friction up the hill
Mm-hmm.
is its maximum friction up the hill.
Okay.
That gives me to find the smallest or minimum mass.
Mm-hmm.
And so I guess what I'm trying to emphasize here is nowhere in this problem did I ever use the minimum amount of friction. You don't use the minimum amount of friction to find the minimum mass. To find the minimum mass, you use the maximum friction up the hill.
Yeah, you use the maximum friction in the opposite direction.
Right. Which I suppose you might call a minimum if you want to do a plus or minus math issue. But I just wanted to make sure that you realize I'm always calculating the maximum magnitude of the frictional force. Whereas I have seen students in the past say something like this: hey, I want to find the minimum amount, so I will use the minimum amount of friction. And they look at this inequality and they put the minimum amount, which is 0, and say, okay, 0 friction. And that's
so I'm just trying to piece this together in my brain. The maximum friction pointing up the hill, just trying to, you know, read the math. The maximum friction pointing up the hill is going to correspond with the minimum weight, because I need the most friction involved pointing up the hill to keep the box from sliding down the hill.
Right.
And then the opposite is true when we've got the maximum weight.
Right. Right. I would kind of say it this way. What's keeping it from going down the hill is both friction and weight number 2.
Tension, yeah. Tension.
So to get weight number 2 the smallest, I want the friction from number 1 to be the most and to be up the hill.
Cool.
Yeah.
Awesome. Yeah, thank you so much.
Nice.
I'm sure you'll see me again today. I'm working on my homework, so I'm gonna go keep working.
Oh, and it's break time. Oh, okay. Yeah, I didn't even realize it was break time. Okay.
Cool. Thank you so much for your help.
All right. See you in a little bit. Bye.